Software-defined networking. Legacy networks have integrated control and data plane within each device, where these devices consist of routers and switches. Here, the data plane is responsible for forwarding the traffic, where the decision on where to forward the traffic among the devices is made by the control plane. The control plane dictates how traffic is forwarded among devices. It is distributed and decentralized across the network devices, where each router may be running a routing protocol such as RIP, OSPF, or BGP to exchange traffic routing information with other routers in a distributed way. The traffic forwarding in these legacy networks is based on destination IP address, destination MAC address, MPLS labels, and VLAN headers only. This is difficult to manage due to the distributed or decentralized nature. Due to the tight integration of control and data plane, the devices are very hard to configure since a network administrator needs to log into each device for configuration. Moreover, the tight integration of control plane and data plane inhibits rigidity, where innovation is difficult. Typically, each vendor has proprietary software and vendor-specific commands to manage the devices. This proprietary software can also be quite expensive. To this end, software-defined networking, or SDN in short, is a novel network architecture which tries to solve the problems faced in the traditional IP networks. In SDN, the control plane and data plane is separated, where the routers and switches just forward traffic as part of the data plane. The control plane is shifted to a centralized SDN controller, which dictates the forwarding behavior of traffic in data plane devices. The traffic is forwarded based on the notion of flow, instead of just a destination. The flow refers to a set of packet field values, where the traffic is forwarded by matching these set of packet field values. Once a match is done, an action is performed on the packets belonging to the same flow, as compared to only destination-based forwarding. The SDN controller is a software which has a fully centralized view of the entire network topology. The SDN controller acts as a network operating system, or essentially a brain in the network where it can control the traffic flows. Multiple network applications run on top of the SDN controller, where they are able to dictate any custom forwarding policies in the network. SDN controller can be used to provision network resources dynamically, in contrast to manual per-device configuration, thereby reducing capital and operating expenditure. For example, the SDN controller may offer services such as L2 VLAN based service from host A to host B, or deploy an L3 VPN from router 2 to router 3, and the SDN controller will automate the network configuration. This enables an ecosystem where developers can build network applications to test custom policies and protocols without worrying on how the network devices are configured. The SDN architecture consists of the northbound API, which is the interface between the SDN controller and the network applications. This offers APIs such as REST, CLI, or even a graphical user interface. This allows hiding complex operations, such as programming the forwarding behavior in the network devices, by abstracting low-level operations in the data plane. The southbound API is at the heart of SDN concept, which is the separation of control plane and data plane. It is the interface between the SDN controller and the network devices, and is usually a standardized protocol to configure the devices. OpenFlow is the earliest example of a well-known industry-standard southbound API to program network devices, where the devices need to be compliant with the OpenFlow standard. The devices or switches use the OpenFlow protocol to inform network events to the SDN controller by using OpenFlow messages. The switches consist of flow tables, which are programmed by the SDN controller with flow entries. Incoming packets are matched to flow entries, which have a corresponding action such as forwarding to a specific port, or even to the SDN controller itself, or drop the packets. These are some examples of the OpenFlow-based flow rules. The first flow rule only matches the VLAN ID in the incoming packet and forwards it to the output port 2. The second flow rule blocks all SSH traffic to the management network subnet by dropping all the packets.